Many important image processing algorithms can be expressed using a high-dimensional Gaussian filter, which mixes values v according to the distance between associated positions p. This framework includes bilateral filtering, where the position of a pixel is a 5-dimensional vector composed of its spatial location x, y, and its color. Pixel values are then mixed with other pixel values that are nearby in XY RGB space. If we wish to perform joint bilateral filtering, in which one image is blurred without crossing edges in a second reference image, we need merely derive the position vectors from the reference image while using pixel values from the image to be blurred. We can be more selective about which pixels are mixed by setting the position vectors to be instead local descriptors. This is the effective denoising technique known as non-local means. Our work focuses on rapid evaluation of this equation using an explicit sampled representation of the space of position vectors. In this framework, we first splat the values into the high-dimensional space at their corresponding positions. Next, we blur within that space. And finally, we slice the space along the original positions to reconstruct an output. Paris et al. In 2006 represent the space using a regular grid of samples and use multilinear interpolation for splatting and slicing. This works well in low dimensions, but as dimensionality increases, multilinear interpolation touches an exponentially increasing number of samples. Adams et al. In 2009 represent the space using samples stored at the leaves of a KD tree. This technique scales linearly with dimension, but requires parameter-heavy randomized tree queries and is superlinear in the number of input values. We instead propose sampling the space at the vertices of a sparsely stored lattice we call the Permutohedral lattice. The Permutohedral lattice is formed by projecting a high-dimensional regular grid onto the subspace in which coordinates sum to 0. It tessellates that subspace with uniform simplices, so for splatting values into the lattice, we can use simple barycentric interpolation. For a d-dimensional lattice, barycentric interpolation touches d+1 lattice points, which is exponentially cheaper than using a grid and does not require any complex randomized tree queries as with a KD tree. For blurring, we use a conventional separable filter, and for slicing, we can reuse the barycentric weights already computed during splatting. The algorithm can be easily parallelized to run on a graphics card. This enables filtering at interactive rates, which was previously only possible for 3-dimensional filters. Here, we show a color bilateral filter, which is a 5D filter, being computed in real time. The user can tune the standard deviations of the filter interactively. We can also run 8-dimensional filters at interactive rates. Here, we show a user denoising an image using non-local means. The 8 terms in the filter consist of 2 spatial dimensions and 6 dimensions of local descriptor, computed using PCA on the space of image patches. In this final example, we use the Permutohedral lattice to propagate local edits to exposure across similar regions in an image. The user paints a coarse mask onto the image, indicating what features should be brightened. This mask is then filtered, propagating the changes across similar regions of the image. The user can also paint low exposure values into the mask, indicating that the exposure should be decreased. Once again, these changes propagate across similar regions of the image. Our algorithm is fast enough to compute at interactive rates, which lets us apply the edits to the image while the user is painting. Here, the user brightens the sky, and now the girl's hair. Next, we decrease the exposure in the grass. And finally, we increase the exposure to bring out the flowers. These propagating edits provide a simple, intuitive tool for making content-aware edits at interactive rates.